Alright, so we're continuing the conversation on base and derived quantities. Last time out we did till 12 and the last one that we covered was pressure. So we're picking up from there, and the first one that we are looking at right now is specific heat capacity. So how was specific heat capacity defined? You might remember this formula, E equals mc delta T. So making C the specific heat capacity the subject of this equation, we get E over m delta T. Again we see E here. So E, if we know the units of already, you can just chuck those in here. Kg meter square per second square. Mass is kg, and temperature, you need to keep in mind this is in kelvins. So kgs cancel out anyway, and you are left with this meter square k minus 1 s minus 2. All of these are basically written as a product, so it does not make a difference what you write first, what you write later. I just like to write them in descending order like this. That's why you'll almost always see me writing the smaller powers in negative first. Next, we just jump on to waves straight away, and in waves, one of those quantities which is not a distance like wavelength or amplitude, and we really need to find the base units of that one, is frequency. And the defining equation for frequency was this, 1 over the time period. So if you're talking about this is going to be 1 over second, and there is no second above, so it's just going to be s minus 1. And you can also see from here that if you were to use if you were to find the base units of wave speed, so that would be f lambda. F is s minus 1, lambda would again be in meters, so that would just give us meter per second, which is the normal units for speed, right? So that idea that any type of the same quantity like force or speed or energy all have the same base unit, that just comes full circle here. Let's do another one, and this time out let's talk about the refractive index. Now again, if you might remember the refractive index from your O levels, then this is defined as sine I over sine R. And in the very first video of this chapter, we discussed that sine of anything has no units. This has no units, and as a consequence the refractive index overall does not have any units. So according to the conditions that we laid down in the very first lecture, this would not qualify as a physical quantity. So not a physical quantity. Alright, next one. Alright, 16. Now we're on to electricity. So we already know electric current is a base quantity. So how if we define charge? Now current is defined as the rate of flow of charge, so I can say the charge flowing is the product of current and the time for which the charge flows. And now for this I know that the current is in amperes, time is in seconds, so this is the unit of charge. Next, if we go on to another one, let's say another important quantity in electricity is potential difference. Potential difference or voltage. Right, so for potential difference, how is this defined? Potential difference is defined as the work done per unit charge, right? And if you might remember, it's also the EMF is also defined pretty similarly. The difference is basically on this criteria that for potential difference it's the work done by the unit charge, and for EMF it's the work done on the unit charge, but the formula is more or less the same, so the units are also going to be the same. So again we see work here. If you remember this, then this does make things very fast. kg meter square per second square divided by units of charge, which are ampere second. So when these go up, kg meter square, the ampere becomes a -1, and there was already a -2 at the top, so -2 -1 makes this -3. Let's do one of the last ones, which is electrical resistance. So for electrical resistance, how is this defined? Resistance is defined as the ratio of voltage to current. So voltage I just found above, kg meter square, A -1, S -3, and current is AS. So when we have this, so this is kg, oh sorry, this is just current, not charge. So this is going to be this. So kg meter square, the only change is with the ampere. -1 -1 makes us -2, and S -3. You might have also studied this. It wasn't really part of the O-level syllabus. It is part of the A-level syllabus, which is the idea of resistivity. Right, so what is resistivity? So resistivity is defined by this formula, where R equals rho L over A. So I can say that rho, the resistivity, is RA over L. So resistance is in ohms, which is this entire thing, kg meter square, A -2, S -3. Area is meter square, and the length is meters. So I can see that kg, nothing happens to this. This is meter square makes us meter 4, and minus the 1 makes us meter cube, A -2, S -3. So that's the base units of resistivity. Now other quantities in this chapter in electricity are energy and power, but using the same idea that we used before, electrical energy and electrical power would also have the same base units as other energy and other power. So the last one, and this might be entirely new to you. If you're an IGCSE student, however, you might recognize this. Right from the archives of space physics, you might remember this formula, Hubble's constant. And if you don't even, that's fine, because most of the times when you are asked to find the base units for something, you would not be given that formula, right? You would not be aware of that quantity, but you would be given some formula which you're going to leverage to find out the base units. So Hubble's constant, how is this defined? This is the speed over the distance. So now if I try to figure out the base units for these, V is meter per second, D is meters, and this just gives us per second. So that's it for this. We've done the base units of a lot of quantities now, and hopefully you now have a feel of how questions like these are to be done. So in the next video, we'll be moving on to more exam type questions, how questions are really asked, and how do we solve those. So see you there.